Okay, here's a problem where we get to study an inelastic collision. In fact, this is a perfectly inelastic collision because the two blocks stick together. So let's take a look at what we've got. There's a block A that starts out at rest at the top of this curved segment. I suppose that's exactly 1/4 of a circle, like a quarter pipe. And then block B starts out at rest. Both blocks have the same amount of mass. It's just referred to as capital M. So there's no numerical values given, but we know the blocks have identical mass. There's no friction at all on this curved surface, but there is some coefficient of kinetic friction on the flat surface. So what's going to happen is block A gets released from rest, slides down, eventually collides with block B. They stick together, and then they continue to move across the surface from point Y to P. So let me erase those markings and start over. Okay, let's get into it. Part A, we have to determine the speed of block A just before it hits. So this is not a problem in conservation of momentum. This is just more a problem in conservation of energy. So for part A, some of you already know the result of this is just going to be V is the square root of 2gh. And in this case, h is nothing more than the radius of curvature. If we extend the curvature, you see it makes a full circle, and it's just falling that far, which would be the radius. All right. So this should be referred to as the square root of 2gr if we're going to use their notation. So let's see where this comes from in case you don't remember. The law of conservation of energy says the energy at point A has to equal the energy at point B. And so the energy at point A is all gravitational potential energy. And by the time it gets to point B, it's lost all of its potential energy and only has kinetic energy. So mgh and 1/2 mv squared have to equate to one another. Mass cancels out, and indeed this results in V is the square root of 2gh. In this case, we're saying h is equal to r. Okay, so we're done with part A. Let's move on to part B. Determine the speed of the combined blocks immediately after the collision. Because this collision is perfectly inelastic, we can start with a statement that says the total initial momentum equals the total final momentum. That means that the mass of object number 1 times its initial velocity plus the mass of object number 2 times its initial velocity is equal to the sum of momentum for objects, so m1 v1 plus m2 v2. So total initial momentum equals total final momentum. However, in this case, we can reduce it a little bit. If the collision is perfectly inelastic, then that means velocity number 1 and velocity number 2 are going to be equal, and we can just call it V and then factor it out. So for a two-body perfectly inelastic collision, the equation that expresses the law of conservation of momentum, it can be reduced to m1u1 plus m2u2 is equal to the product m1 plus m2 added together times final velocity v. And so again, we're just using that same notation where u is a symbol that means velocity before a collision, and v represents velocity after the collision. Let me switch pens so I can write in specifically how it relates to this problem. So that's a very general equation for any two-body perfectly inelastic collision. However, in our case, mass number 2 was at rest, and M1 we're actually calling capital M. Okay, and then right before the collision occurs, we found that its speed at the moment just before it strikes the second block is the speed of the square root of 2gr. So then when they stick together, now you have a mass of 2m, and then with a velocity of v. So we can cancel the m on both sides of the equation, and it looks like the final speed of the two blocks is 1/2 of the square root of 2gr. If we want to get that all together, we can say is the same thing as the square root of 1/4 times the square root of 2gr. And so the end result is it's the square root of gr over 2. So there's our answer to part B. Let's scroll back up and carefully read question for part C. Determine the amount of kinetic energy that was lost due to the collision. So if the collision is perfectly inelastic, then that means there's always going to be some amount of kinetic energy that's converted to heat. It's only in the elastic collisions that no amount of kinetic energy is lost to thermal energy. So let's figure out exactly how much kinetic energy was lost. So let's figure out what the initial kinetic energy was. It'd be 1/2 times capital M times U1 squared, although U1 is the square root of 2gr. So we get an initial kinetic energy of 1/2 times M times 2gr. Well, of course, that's what we get, right? The 1/2 and the 2 cancel out, and we just get mgr, which is equivalent to mgh if we were expressing it in typical terms. And the initial kinetic energy right before the collision would have to match, you recognize this as potential energy, because, once again, the curved portion of the track has no friction, so none of the potential energy at point A is lost as it's converted to kinetic energy at point B. All right. So what's the final kinetic energy? The final kinetic energy is 1/2 times a mass of 2m, and times the final velocity squared, but the final velocity is the square root of gr over 2. So our final kinetic energy is m times gr over 2, or mgr over 2. So it looks like the final kinetic energy is equal to 1/2 the initial kinetic energy. Okay, let's think about this final result that we're getting. It says the final kinetic energy is half of the initial kinetic energy. Now, in general, kinetic energy is 1/2 mass times velocity squared. Well, in this collision, the mass went up by a factor of 2. Velocity went down by a factor of 2, or we'll say changes by a factor of 1/2, but that quantity gets squared, so velocity squared is going down by a factor of 4. So when one quantity goes up by a factor of 2 and the other goes down by a factor of 4, the overall net result is that the kinetic energy goes down by a factor of 1/2. Now let's just make sure we're answering the question in the way it was posed. Determine the amount of kinetic energy lost due to the collision. So we've stated it as a ratio. We've said half of it is lost, but they want it expressed as an amount. So the initial kinetic energy was mgr, and since we lose half of it, then our loss of kinetic energy is mgr over 2. Okay, let's move on to part D. Actually, part D of this question references specific heat. You might know from a chemistry course or a previous physics course that you've taken that heat is equal to mass times specific heat times change in temperature. If you want to attempt this problem on your own to try to figure out what the temperature change is, if you're given the specific heat, you're welcome to try it, but we would actually reserve that problem for study of physics 4C in another semester. But we can answer part E, determine the additional thermal energy that's generated as we move from point Y to point P. Let me clean up the document a little bit. Okay. Determine the additional thermal energy that's generated. So let's write in some of the answers we already know. The answer to part A, the speed just before they collide is the square root of 2gr. The speed immediately after the collision is the square root of gr over 2. The amount of kinetic energy lost is mgr over 2. We're skipping part D. Let's get a little room to operate here. So thermal energy generated is equal to work done by friction, and work is the product of force and displacement. So a force of friction is coefficient of friction times normal force, and then we've got a distance d. Actually, if we look at it carefully, they're calling it L instead of d. If we were to make a free body diagram for the two blocks as they're moving from point Y to point P, there's a normal force pointing up and a gravity vector pointing down. This would be not just mg, but 2mg, since the two blocks are stuck together. So the amount of heat is equal to mu times normal force, which is 2mg, and times a distance of L. So there we have it. Q equals 2 mu capital mg L. So let's summarize. So our answer was 2 mu mg L for part E. And let's be clear about this one. That amount of energy that's converted to thermal energy is not the Q of the collision. So we have a block that slides down this ramp, no conversion of mechanical energy to thermal energy along the track, and then the two blocks hit and collide. In that process, some mechanical energy will be converted into thermal energy, but that's not the thermal energy we found here. From that point on, even more thermal energy is generated, and ultimately the two blocks come to rest. And so maybe we'll call this a Q1, the amount of thermal energy generated in the collision, and then we have a Q2, the, what do they call it, additional thermal energy that's generated due to the force of friction as the blocks slide across the surface. I think the big takeaway of this problem was the part in which we applied the law of conservation of momentum that said as long as we have a two-body collision, we can state that m1u1 plus m2u2 is equal to the quantity m1 plus m2 added together times a final velocity v. That's a pretty good general equation anytime you have two objects that collide and stick together and conserve momentum.